A modern robotic surgical pincer can lock into an exact angle, executing its complex movements with near-perfect mechanical repetition. That hardware execution relies entirely on how the system interprets live data streams. The surgeon at the console is responding to high-resolution endoscopic video and real-time kinematic sensor feedback processed by artificial intelligence. Yet, while the hardware is rigid and precise, the surgical environment is entirely unstable. Patient anatomy, tissue deformation, bleeding, and changing lighting conditions are highly dynamic variables that refuse to stay constant. This clash between static algorithms and a fluid environment triggers the primary failure state for medical AI: model drift. Model drift is the progressive, often silent degradation of an algorithm's predictive accuracy. Over extended operational periods, the model's output steadily diverges from clinical reality. Standard software fails from code defects or unexpected server crashes. Machine learning models simply decay as a statistical inevitability. When the statistical properties of the real world drift away from the data the model was trained on, the math breaks down. A model validated in a controlled laboratory setting will behave very differently after 6 months of exposure to the unpredictable variations of a live operating room. Securing patient safety in robotic surgery requires abandoning the assumption that validation is a one-time event. We have to build continuous mathematical observability directly into the surgical workflow. This scatterplot represents data drift, specifically covariate shift. The model's logic remains intact, but incoming variables shift from the baseline. In the OR, this manifests when patient demographics change or robotic sensors undergo physical degradation. The second, more dangerous classification is concept drift. Here, the underlying relationship between the input variables and the actual outcome changes. The target moves. Concept drift happens when the clinical ground truth evolves. If an institution introduces a new protocol, or authorities update criteria for a successful resection, the model's previous understanding of success becomes objectively false. These shifts have distinct temporal signatures. An equipment firmware update might cause a sudden, systemic shock to the data pipeline, whereas evolving disease patterns cause slow, incremental degradation over months. If you detect a performance drop and blindly retrain the model without knowing which specific type of drift is occurring, you risk compounding the error and actively worsening the system's performance. Targeted recalibration requires a precise mathematical taxonomy. Without it, the hospital is blind to exactly how and why the system is failing its patients. This is not a theoretical exercise. Longitudinal analysis of deployed AI systems reveals hard clinical data documenting performance decay. This chart tracks pre- and post-drift AI performance across 4 major surgical domains. We see measurable predictive drops in laparoscopy, cardiac, neurosurgery, and orthopedic models over extended timeframes. The degradation is acutely visible in high-stakes fields. Neurosurgical models recorded a 4% drop in accuracy, while orthopedic models degraded by 6%. These are not artifacts of random variance. The statistical analysis yields a p-value of less than 0.0001 across all specialties. Furthermore, an analysis of variance tests the severity of the drift. The resulting F statistic for the drift effect is a massive 233.950. That number proves variance between pre-drift and post-drift conditions far exceeds the normal variance of operations themselves. Performance degradation is a systematic, universal phenomenon. A 5% drop in neurosurgical model accuracy translates directly to misidentified anatomical landmarks and incorrect real-time guidance. It is a measurable escalation in patient risk, requiring immediate intervention. To prevent that risk from reaching the operating table, engineers deploy live equation engines. These systems compute distribution distances in real time, catching drift before the first incision. This graph compares 2 cumulative distribution functions using the Kolmogorov-Smirnov, or KS, test. It measures the maximum distance between the model's expected behavior and the actual live data. The KS test constantly evaluates that divergence against a strict mathematical threshold. If the gap breaches the critical value of 1.36 over the square root of n, the system triggers a hard alert. For highly complex, multidimensional imaging data, we utilize maximum mean discrepancy. This maps data clusters using a radial basis function kernel to track nuanced visual shifts that a simple linear test would miss. We track the population stability indexed, calculating the shift in distinct data bins over time to locate exactly which variables throw off the math. All three of these algorithms ingest raw kinematic and visual data directly from the robotic arms in the background of every single procedure. Running these tests requires a heavily optimized computational architecture. The system evaluates millions of data points simultaneously without adding a single millisecond of inference latency to the surgeon's console. The equation engine acts as the ultimate failsafe. It takes silent, invisible degradation and forces it into hard, actionable alerts. But raw mathematical alerts are clinically useless if they exist in a vacuum. They must be structurally integrated into the operating room's standard workflow. This diagram maps the preoperative sequence. The surgical checklist now includes an automated health check on the AI itself, pulling recent drift events to determine the system's status. Before the procedure begins, surgeons receive a definitive verdict. If the algorithms detect severe concept drift, the system hits a hard hold, preventing the use of unvalidated guidance. To fix a flagged model, engineers use a shadow mode architecture. This runs a newly recalibrated model in Track B, perfectly parallel to the degraded live model in Track A. Shadow mode safely compares the outputs of the new model against the old model using live surgical data, completely decoupled from the actual surgical decisions being made in the room. The final requirement is human-in-the-loop validation. Expert surgeons manually review and annotate the specific edge cases that cause the statistical alert, confirming whether the model's new logic aligns with clinical reality. By linking these systems together, a hospital guarantees that no recalibrated math ever touches a patient without explicit, parallel-tested verification. All of these mechanisms, the statistical tests, the pre-op gates, and the shadow comparisons, are synthesized into a centralized model registry. This registry acts as a version-controlled vault. If a newly deployed model exhibits sudden behavioral anomalies mid-surgery, the system can instantly roll back to the last known stable baseline. These technical safeguards are enforced by a strict legal reality, permanently recorded in an immutable, unalterable digital audit log. Global health authorities enforcing standards like the FDA's 510(k) and the EU Medical Device Regulation require rigid oversight for deployed AI. Because post-deployment degradation is an empirical certainty, compliance mandates continuous observability. Regulators expect hospitals to prove their algorithms are still accurate months after installation. Even the most advanced drift detection metrics carry a 7 to 14-day detection latency. Automated adverse event logging bridges that gap, tracking every fractional drop in precision. The modern robotic suite is an integrated loop: live statistical monitoring, strict clinical gating, parallel shadow validation, and continuous regulatory logging. Artificial intelligence in healthcare is not a static tool you install and forget. It is a dynamic, rapidly evolving mathematical system that demands continuous, rigorous management to maintain the safety of the patient.